Hello, my name is Braden Stump, and I'm the Director of Product and Business Development at Aerosol Devices, a division of Handic Scientific. And today I'm here to talk to you about aerosol sampling. More specifically, I'm here to talk to you about the specific licensed technique that Aerosol Devices makes our instruments from. So, water condensation and growth tube sampling. I'm looking to give you an introduction to the technology and kind of answer a few core things. I'm looking to answer, one moment, why aerosol sampling is important and why users would choose this water condensation growth tube sampling technique. Looking to address how these water condensation growth tube samplers, how they operate, how they address aerosol sampling needs and difficulties, and also how they compare to other technologies that can also sample aerosol. This isn't a new thing by any chance, right? And then finally, I'm looking to address what the different instruments that we at Aerosol Devices offer and how we manufacture them and how they differ from each other and address scientific needs. So hopefully this will be useful. I'll have this as a tagline at the end, but please also feel free to reach out to us at Aerosol Devices to ask more questions. I won't be able to cover everything, but this will be a nice top-level overview, some dipping into the theory, some dipping into the instrumentation, and some dipping into the need of why this all matters. And speaking of the need of why this all matters, we'll first start with why aerosol sampling is important and why a user would want to choose our technology to solve that purpose. So first and foremost, asking the question that I believe a lot of people are asking right now: why do we care about aerosols? I think that with glossing over this slide, most people agree that bioaerosol laden diseases such as COVID-19 or other pandemic-based bioaerosol laden diseases are big deals, issues in our world, and we're looking to learn more about them. But even past that, pollution is something that carried in the air is of great concern to people researching, doing studies, but also even businesses wanting to learn more about what's going on. There are, I think, openly a lot of things in the air that we look to learn more about and study. It's what we breathe. It's what we spend all of our time in. And so it makes sense that we would need instrumentation well suited to pull it out of the air to do downstream processes, quantifying, qualifying, characterizing, learning more about it. So moving towards kind of the why and how it relates to our technology, aerosols, and especially specifically bioaerosols, can be very difficult to sample in a way that you can do science or learn more about them from. I mean, you look at, for example, size dependent going into the nanometer size range, extraction efficiency. So the ability to capture and then extract from a surface or liquid where you've sampled, that starts to become an issue. You start to have, going lower and lower in size into the nanometer range, issues with actually capturing enough particles, capturing enough of a percentage of particles, extracting it from however you're sampling it. Additionally, if you're sampling into something that is, diluting itself over time, you worry about your limited detection on your downstream process where you're taking this aerosol sample. Also, I mean, for not all sampling techniques, but you do worry about sample contamination, contamination concerns, ability to clean and decontaminate instruments. Those are all pretty big, especially in the bioaerosol world. And then finally, you also look at, sadly enough, sampling methods compromising the integrity of your sample, exposing it maybe to high heat or a lot of, a liquid or solution that you wouldn't want to expose it to could degrade the integrity of what you're trying to sample as you're sampling it. And you'll see on the right here a few different common aerosol sampling methods, and they all have their benefits, right? They've all been utilized before to great effect. But you can understand that throughout that process they would have some difficulty in sampling that would require there to be a need to be filled. So drilling down a bit further past that point, going from bioaerosols to viable bioaerosols, sampling something active, making sure that it's not inactivated in the sampling method. You're wanting to see transmission of a live bioaerosol, quote unquote, depending on what you're sampling. And that can be even more difficult. specifically because the methods by which a lot of sampling occurs can expose bioaerosols to desiccation, so drying out, mechanical stresses from being potentially shot out of a nozzle or an impinger to get into a more concentrated sample, and then also thermal shock, right? Some of these methods require large amounts of temperature, heat, in order to move these smaller bioaerosols into something that can actually be captured or be analyzed. So the trick, with viable bioaerosols is even a step further than that in difficulty. That said, so the water condensation growth tube sampling technique that Aerosol Devices manufactures and license has three primary niches, three primary abilities that really make it competitive compared to this technology. And that's kind of what I wanted to start with as the core of this presentation. Specifically, the first of those three is efficient capture of nanoparticles, greater than or equal to 5 nanometers. The real range of particles that we can sample across is from 5 nanometers to 10 microns, a very wide range, all with effectively even and high collection efficiency, which is great. But you don't see a lot of more traditional techniques being able to sample into this low of the nanoparticle range with that high efficiency, which can be useful not only in the bioaerosol world, but in the semiconductor industry, in aerosol science and aerosol chemistry. And for many of these downstream techniques here in this wheel that you're pairing your sampling with, nanoparticles matter. They exist, they get deeper into your lungs, and they're just harder to pick up by a lot of conventional techniques. The next of these three primary niches is specifically viable capture of virus, bacteria, and other microbes. You can also sample into genomic preservative with our technique and do genomic preservation, so DNA and RNA being retained. But one of the things that we do like to highlight is if you are looking to do a study that needs to know viability, it is a rare thing that a sampling technique is gentle enough to capture bioaerosols viably, retaining infectivity, retaining the ability for it to be cultured, things like that. So that is something that we've been really excited about as a more recent development that we've been trying to accommodate in our samplers for this bioaerosol method. Finally, as a high point, we also look at concentrated and convenient samples. Some of these samples, you think about sampling onto a filter, the most kind of rudimentary comparison to our technology, and how hard it is to extract off of a filter. A lot of times you're exposing it to some wash or solvent that's going to dilute it. And our technique has this really specific advantage of having not only a concentrated sample, but having these convenient methods, sampling into these small liquid vials, sampling onto solid substrates or microscopy surfaces that are immediately ready to hand to downstream techniques. So those are the three things that we're most proud of. There are other benefits to this technology, but these, I believe, are the three that really have us stand out compared to competitor technology. And also what makes the science done with our instruments by our collaborators and users and customers so high quality. Cool. So first, talking about the efficient capture of nanoparticles, but also all particle sizes. We'll be bringing this graph up again when we talk about the theory of how our instrumentation works. But that said, if you look here, this is the water condensation growth tube sampler collector. CGT or condensation growth tube is used interchangeably. Comparing our technology to two different aerosol or bioaerosol sampling techniques, you can see with particle diameter here at the bottom, so size of particles from 5 nanometers to 10 microns, and then collection efficiency, this is effectively 100%, 50%, 0%. You can see over a large variety of particle sizes, but especially going into the nanometer range, you see this benefit of this very consistent high efficiency bioaerosol and aerosol generally capture. Specifically, a lot of people utilize our instruments for capture of viruses and viable viruses at that, because competitor technology, once again, not using the same technique that we do, falls off with their capture techniques below about the 1 micron point. So we really like to tout that nanoparticle, that consistent capture across a wide size range. Additionally, just highlighting the viable capture before we get into the theory. Viable aerosolized capture is superbly interesting, and kind of one of the papers that has been the most exciting for us as far as our technology being really vetted in the field is this paper from John Lednicki at University of Florida, looking effectively and being able to capture in a field environment in a hospital viable SARS-CoV-2. It was a smoking gun style paper that was the first instance of captured viable, aerosolized SARS-CoV-2 in a peer-reviewed research setting. It was extraordinarily well done. It utilized our BioSpot Vivis bioaerosol sampler, which we'll talk about soon. But there have also been plenty of other, capture of other viable bioaerosol. Great. And then the last thing, this concentrated and convenient sample collection. I'm not going to talk about all of these in detail because we'll discuss them further down when we talk about each of the different samplers. But we really have tried in the design of our instrumentation and how it works to look at convenient methods of sample capture. So you can look at 500 microliter and below liquid vials. You look at sampling onto these solid well plates that can have substrates inside of them, even like aluminum foil, or it can be transferred to an auto sampler, or it can be taken to a microscopy step from there. SEM stubs, TEM grids, microscopy stuff that you can just hand right off to the next step in the process. And even genomic preservative soaked swabs, so that, effectively break off into the PCR vial, lyse it and send it to the downstream processes from there. I think, our method of sampling, which we'll talk about in just a moment, really allows for a lot of flexibility and convenience in how you're handling your sample, which, ergonomics wise can be a big deal. Great. So on to step two and part two of this presentation more so. And that is how these water condensation growth tubes, how they operate, how they address aerosol sampling needs and difficulties. This is kind of the theory section. And I will be kind of not, going with the high points, the 10,000-foot view. But if you'd like to learn more about this, I'd also be happy to describe further meeting up for Zoom and beyond. Effectively, there is this technology that we license is its core is a thing called a condensation growth tube. And this water condensation growth tube sampling technique is something that our team licensed from Aerosol Dynamics. So thank you to the whole crew over there, Suzanne, Aranza, Steve, Greg, Nathan, everybody. But the core of it is it mimics the human lung. It is a kind of a system that, or it is a tube that is based off of three governing systems that are pretty gentle and easy to actually work with. So I'll move on to this slide to discuss that. But what you see is that there is an airflow system, a wet wick system, and then a temperature control system. So these three main systems that allow for high efficiency capture of particles. So looking at this model over here on the left, you'll see a wet wick that is maintained, wet with some water injection pumps. So it's just kind of a hollow tube with a wet wall on the outside. And then you have airflow, where your sample inlet is pulling in aerosol. This is laminar flow in this tube. It is gentle movement, continuously through this tube, where you can see aerosol anywhere from 5 nanometer to 10 micron being pulled in. And then finally, you've got these temperature stages. And this cold stage here, the conditioner kind of gets everything cooled down and pulls a little bit of water vapor to the walls, gets everything kind of uniform, regardless of the external environment. And it is this jump from this 5 degrees Celsius to this 35 degrees Celsius, this warm initiator. More specifically, it's the delta T between this region. This change in temperature with this wet wall, you get super saturation in this region. Effectively, there's a fog here, right? And particles as small as 5 nanometers, in the case of our instrumentation, it forces condensation around them, forming a droplet. And that droplet grows throughout the rest of this water condensation growth tube, forming this larger, depending on the size of the instrument, approximately 3-4 micron droplet. And that 3 to 4 micron droplet is easier to capture inertially into liquid, onto solid surfaces, onto swabs, onto SEM stubs, TEM grids, the whole shebang. So what this is it is a method to grow and surround particles in water via effectively natural processes. There are some huge benefits to this. The first being, with this blanket of water around the particles, you are getting really pretty gentle impaction. So when it actually hits the surface, that bubble of water around it is taking a lot of the stress of impaction. You don't have to impact it as aggressively because you have this large droplet around it that will allow you to impact properly. So that is really a benefit, and that's one of the reasons we think that viable bioaerosol capture is possible with this technology. Additionally, you'll see from this first graph up here from Herring et al. That along the actual center line, 55% of the radius, 75% of the radius sort of graphing here, which is temperatures inside the growth tube, the actual wall temperatures you see here is not aligned. It's not the actual temperature of the airflow, the majority of it itself. What that means is that you have this moderate sample flow temperature and a pretty fast residence time. So you're not thermally shocking your aerosol very much. The most that it's seeing is 30 degrees Celsius, but the residence flow through this section is, well under a second, 0.3 or 0.03 seconds. You can follow up with me for that exact information. I do not have it on hand currently. And then finally, the benefit of the third stage, this moderator stage, is to control your outcoming water vapor. You can cause it to maintain liquid level. You can cause it to really dry out afterwards as your droplets are growing to get this nice, dry sample impaction onto substrates. It's bounce free. It's soft inertial impaction onto any surface, because the final thing that matters, all that you need is the right distance from this jet of this nozzle to this liquid or solid substrate, which means you can put really anything below it that kind of aligns with that specification, which ends up being very flexible. Bringing up this graph again, that theory is the reason why you see this 90% and above capture, regardless of size of particle here. It's kind of the thing that we like to tout the most, which is that over this huge range of particle sizes, you're seeing the same efficiency. Great. I'm going to hit the next. Cool. Finally, we are on to part 3, which is how, utilizing this theory, utilizing this technology, the current different classes of instruments that Aerosol Devices manufactures, and then some examples of how they address scientific needs. So going to stay on this slide for a while, so take it in, take a screenshot of it if you need to. Aerosol Devices currently, as of today, June 5th, 2023, has 3 primary product lines that all do effectively the same thing, have the effectively the same collection efficiency, but are different in flow rate and then sampling substrate. And I'm going to talk about them now. The first of these 3 instruments is the BioSpot Gem. It is our smallest. It's also our newest. It's our most price competitive instrument. Our instruments go the BioSpot Vivis, and then the Spot Sampler is more price competitive, and then the Gem is even more price competitive from there. It is our smallest, has a flow rate of 1.2 liters per minute, and can sample onto swabs. It can sample into liquid vials. It can sample into a solid well. This is, refined, easy to use, easy to clean, portable, single position sampling, if that makes sense. Smallest, it is the one that you would take, out to a field campaign, especially, chamber studies if you don't need higher flow. The sample is still very concentrated, which is quite useful. And the BioSpot Gem, but also all 3 of these samplers, as a small caveat, all 3 of them, when sampling into liquid, have a collection efficiency of 90% of particles, 5 nanometers to 10 microns. When sampling onto a solid surface, like a well or SemStub, have a collection efficiency of 95% of particles, 5 nanometers to 10 microns. A big asterisk there. This is concentration dependent, of the concentration of aerosol that you have. More specifically, once you get above that 10 to the 5th numbers per cc range, we aren't able to promise that collection efficiency. That effectively is saying don't smoke a cigarette into the inlet of your instrument if you're sampling in an ambient environment. But if you are doing chamber studies, you'll have to think about how dilute you need your aerosol in the chamber, how much, if you need a dilution bridge or mixing air or other things like that. But that said, moving from the BioSpot Gem to the Spot Sampler 110B, The spot sampler is a little bit less, industrial health, indoor air quality aimed compared to the BioSpot gem. The spot sampler is the most flexible, I would say, and also our oldest instrumentation line. So it's slightly larger, 18 pounds compared to the 10 pounds of the gem, about double the volume. But it has been utilized in aerosol chemistry, aerosol science, bioaerosol runs. It has specifically, its niche is time resolution in sampling. So there's a time-resolved solid well or a time-resolved scanning electron microscope stub tray that can rotate between positions to sample into, but it'll also sample into singular liquid vials as well. So its flow rate is 1.2 to 1.5 liters per minute. And more than anything else, it has been used in quite a few studies, but is the most kind of flexible for different experimental needs of the three classes of instrument. Finally, on to the big one. One of the most published of our instruments, and also the one that has the highest flow, is the BioSpot Vivus. So this is our largest sampler. It is 53 pounds, and then its size is here, so 30 inches tall, so it is the largest of the three. However, its flow is also the largest. It can flow between 8 and 15 liters per minute. So a wide range, but also much higher flow, almost 10x depending on the flow rate that you're operating at compared to the gem or spot sampler. And it samples into 35 millimeter Petri dishes. As a kind of reminder from what we talked about in the theory section, the liquid that you sample into, you have to wet the walls with water, of course, but you can sample into any liquid you'd like in your Petri dish or your vial. So genomic preservative, artificial saliva, acids and bases for chemistry stuff, PBS, your buffer of many different kinds, agar, anything that is convenient to your sampling technique should be perfectly fine for sampling into liquid. All three of these instruments actually can sample into liquid. But that said, this is a rugged instrument. This has been used in ambient sampling. This is specifically the instrument used in that smoking gun COVID study, viable H1N1, viable MS2 capture campaigns. And that's not to say that the spot sampler and gem cannot do that. They have similar concentration of liquid sample, but folks really like the higher flow and the rugged design for these more intense sampling campaign environments. Once again, if you have questions on specifications with these instruments, please feel free to reach out to me as well, and I can provide you more granular information there. Cool. So I'm just going to go into a few use cases of each of those three samplers just to give an idea of where these samplers could be utilized. Courtesy of Marina Nieto Caballero from Colorado State University. She has utilized these instruments out in Nunn, Colorado. You can see them being used here. And then you can also see uses of the swab-based sampling breaking off into these PCR vials, the solid position well sampling, and liquid sampling as well. We've seen folks use these instruments in portable field campaigns where they're easy to use. We're aiming for it to be easy enough to use in industrial health, indoor air quality applications. And you kind of have a wide array of single sampling methods here. This isn't automatically time resolved. You'll need to swap between samples. And then there are plenty of folks utilizing these instruments that are close to publication, but not a large depth of publication here yet, primarily because it's brand new. So we're really excited about it and think that it is going to be a nice addition to our product catalog. Additionally, looking at the spot sampler, the SS110B, the spot sampler and the BioSpot Vivus being around for a long time, have a large depth in the catalog of references and publications there. Just wanted to demonstrate, as we talked about before, the flexibility of of the spot samplers sampling techniques. A recent paper out of Virginia Tech from Hawks et al. In utilizing actually hamster enclosures, utilize the spot sampler to capture viable SARS-CoV-2, which is extremely interesting. So there's the bioaerosol application. You'll see the aerosol chemistry aspect. Aranza from Aerosol Dynamics has done a few different papers showing aerosol chemistry capture, doing downstream sampling with auto samplers and things like that. And I mean, also Aranzo is part of the team that originally developed this technology in the first place, right? So it's good. Uh, but then other, plenty of studies all over the place, from Raman spectroscopy to sea spray aerosols to literally being on a ship at Scripps Institution of Oceanography, has been using the liquid spot sampler to detect enzymes in aerosol along California as well. So a very jack of all trades, Swiss Army knife sort of sampling instrument. Cool. And then there will be a few slides on this one because I really like being able to show the graphs here. The Biospot Vivis, as we talked about before, was utilized for that first time around in first proving that SARS-CoV-2 can be captured viably. But it is, the workhorse that we have seen for ambient, viable bioaerosol sampling. It's rugged. It's got the higher flow options. It is typically used in more of a research setting compared to stuff like the Biospot Gem, for example. But stuff that we like to highlight, for example, if you'll look at this study from Mauha Pan, you will see compared to the SKC biosampler, which is a comparably used bioaerosol sampler for sampling viable MS2 bacteriophage in air, you're seeing about a 10 times increase in the amount of viable capture here for the water condensation growth tube, in this case, the Biospot Vivis, compared to the SKC biosampler. On another run here as well, in John Lednicky's paper sampling viable H1N1 influenza. Sorry about the spin there. That probably doesn't show up well on the Zoom recording. But for a variety of different tests, comparing the SKC biosampler here to the Biospot Vivis, the water condensation growth tube collector, plus or minus the error bars given, you are seeing about a factor of 10 increase in capture of infectious H1N1. So this is really, I mean, it just goes to show, and there are plenty of papers of the Biospot Vivis being able to capture infectious virus and bacteria, that this is really that ambient, viable bioaerosol capture tool. And we are very proud of that, and we try to make sure that we maintain that integrity in each instrument that we manufacture. Cool. So finally, the last thing that I wanted to do before I close here is talk about experimental setup. An aerosol sampler, like any tool, is only effective as the skillfulness of the hands that wield it. And honestly, we have seen people from all different walks and industries of folks wanting to do aerosol sampling be very successful with these tools. That said, aerosol science is tricky. Sampling aerosol is tricky. There's things like static that build up in tubes that you can lose samples even before entering the inlet of the instrument. So I wanted to take this point to highlight, please feel free to contact us for ways to come up with or improve your aerosol experiment to better use these samplers. Please feel free. It is my job to make sure that anyone using these instruments is successful. So we're looking forward to you all reaching out and making sure that, it is our goal as a company to make sure that if you are setting out to complete an experiment to answer a question, that our tools are able to do their job and to do as they have promised on their specifications to help you achieve that. So please feel free to reach out. Finally, I just wanted to say, if you have questions, my email is at the bottom left-hand corner of the screen, but also reach out on our website, reach out to us on LinkedIn. We are here to help, and I hope that this has been helpful. This has been a presentation and learning more about specifically water condensation growth tube samplers and beyond. So we're looking forward to hearing more. Thank you again for your time.